All right. Hi, everyone. I'm here to tell you about some of my favorite areas of quantum computing. And what I'll tell you about today is the importance of electronic structure, try and give you some motivation, some concepts there. This is a summer school that includes a wide range of backgrounds, so I'm going to give very much a cursory overlook of kind of how these ideas fit into the larger ecosystem. What you'll see tomorrow in Module 10 is the shortest factoring algorithm. What we want to do today is give some other application areas that we're not going to be able to get into during the course of this summer school. So with that in mind, one of the important applications that people have discussed about quantum computing since the beginning of quantum computing is this notion of quantum simulation for quantum computers. Right? So with that in mind, let's move to the first slide. So yeah. So what I want to do today is kind of go over some of the things that we've already discussed. We discussed quantum mechanics at a very detailed level. You guys have gone through some linear algebra. You've gone through some basics of how quantum states work, how quantum systems work. So we're going to try and keep that alive and try and think through how we can actually apply that to some situations that we're interested in. And some situations that might be interesting from an industrial standpoint. So, yes, perfect. Okay, so what quantum chemistry is about is trying to take this idea of having a computer that I can understand a lot of things with, right? So we have computers that compute algorithms. You guys are looking at the Deutsch-Jozsa algorithm, which is deciding if a function is balanced or not, right? In a much more complicated situation, you might want to know something much more about a function, right? So if the function perhaps is a molecule, here we have anthracene, which would be our toy molecule for the day. So this toy molecule, you're going to somehow discretize it, come up with a computer program, and that computer program is then going to be used to compute different things about the experiments and chemical reactions that might occur. So the idea is that instead of actually going to the lab, instead of actually going to get your hands wet, instead of going to set up a whole, chemical reaction and trying to go through everything and figure out what the products are, what the reactants are, and trying to put everything together and trying to go back and characterize everything bit by bit. Or you get some characterization from, some other program, from spectroscopy or from MRI or these different techniques that people use. So instead of doing all that, John Popel, who won the Nobel Prize in 1998 for chemistry, along with Walter Kohn, develops this idea of model chemistry. Model chemistry is this idea that we're going to take a set of equations, we're going to take a formulation of those equations, we're going to take an approximation of those equations that we can compute numerically, and apply it to all molecules as much as we can. We're going to try and see if we can understand things about the molecules, understand things about the reactions, about whether the reaction would occur, whether the reaction wouldn't occur, what are the properties of the reactants, what are the properties of the products. Okay? So this is the main idea of what you want to do with computational chemistry. John Popel develops this program called Gaussian, where you can see a little bit of a snippet here into the background, which is a bit far afield from what we're doing here in our summer camp. But the idea is we're going to try and connect these things, at least at the high level, and leave you with some directions you can go on after the summer camp. Okay. So then, right. So why do we actually want to compute these different things? Why do we want a numerical approximation of these different aspects of a molecule? Well, we want this idea of electronic structure. So electronic structure, I don't know that it's worth getting into all the details, but when we think of a molecule, we think of water, we think of anything else, well, it's vibrating, it's moving, it can be different conformations, it might vibrate, it might absorb light, it might emit light, it might have some rate of reaction, it might have some different pathways to go through reaction. And what we have here on this side is just a sketch of the energy surface. So you see here on the side is energy. So the major part of what we want to understand about molecules and molecular systems is what is the energy of the electrons. So these electrons are going to be the quantum particles we're thinking about. These quantum particles move around nuclei, and they're moving around, and they're going to dictate what these beautifully colored surfaces look like. What these beautifully colored surfaces are the things that are going to tell you what geometries are going to be lower energy, which geometry is going to be higher in energy, and all this is going to be determined by how the electrons respond to where the nuclei are. Okay, so I guess it's not very big? Yeah, I can zoom in a bit. Okay. So for instance, in this case, you can see here what this picture is this is a picture of extending the bond between this one and this one. So if you go along some pathway, you can say inside of a nice low energy situation, but if you try and go inside some other direction, you're going to go up in energy and it's going to be prohibited. So when you ask how's your reaction proceed, it'll proceed along this long pathway where it goes in here, it goes back out. For this one here, you can see some sort of rotational surface. So as you rotate the molecule, it goes above a barrier, below a barrier, below, through a barrier, below, above. So you can imagine these water molecules rotating, and as they rotate, it's going to change the potential energy of the system. And the question of how that potential energy changes is exactly what electronic structure is about. Over here, we have some sketches of reactions. We have A, B, C being some reactants. We have some molecules. The vertical arrows are corresponding to absorbing light. Okay, so you're absorbing light. So you see here it says photoelectric. So this is the photoelectric effect. So you have photons impinging on this, and it's going to cause some excitation. Here we have different reaction pathways. You can have A plus BC, and this will be our reaction. We talk about the energy of reaction is here. There's a barrier height to how quickly you can achieve this. And all these things here that are drawn, all these lines, all these curves and everything are computed. These aren't just sketches of what we think it looks like, or you open up your chemistry textbook, you're like, how do they know this? Right? How do they know it? By solving equations. Okay? What equations they solve? This is where we come right back to where we are in our course. So, what equations are we solving in order to understand these concepts? It's looking at Schrodinger's equation. So Schrodinger's equation, just as a reminder, is that we have some sort of way of dictating how the system will evolve. The system is going to be composed of two parts, two energy parts, some kinetic energy and some potential energy. Not so important what they are, but in the end, this H here is going to represent an energy operator. So it's the observable associated with the energy of the system. So as the energy of the system, it also tells us how the system will evolve in time. So this is a differential equation. This is the time derivative of the wave function. It's telling us how the wave function changes in time. Or we can solve the eigenvalue problem, which Eric discussed quite well in terms of what eigenvalues, eigenvectors are. So we want to know either the eigenvalue situation, or we want to know how to use this same H. So this is the H here, and the H here. That's the sum of kinetic and potential energies in order to know how either the system evolves or what energies are going to be the lowest energy, the second lowest energy, and so on and so forth. Okay. This is just a very big picture of what we're thinking about here in terms of quantum mechanics, not necessarily quantum computing, and we'll zoom back into quantum computing in a few minutes. But first, let me just take a second here to make sure that everyone at least has a big picture of what we're talking about.
Is the Hamiltonian always involved with energy?
Yes. Yeah. So it's actually defined as an energy operator. It's almost always defined in terms of energy. And in fact, the Hamiltonian is exactly how you define the energy of the system. So you have a system that doesn't have the Hamiltonian as determining the energy, then it's not the Hamiltonian for that system.
And then the Schrodinger's equation is basically telling us how the particle reacts to the wave function, or I should say how the wave function reacts. I'm not sure. What do you think?
So that's a good question. So let me slow down. Why is the Hamiltonian a matrix? So it's a matrix. Well, it's a matrix for a variety of reasons, but you want to think of it as an observable, as any other observable in quantum mechanics. In this case, the observable that's preserving our energy. This operation that's preserving our energy, this Hamiltonian, is going to tell us what the energy of each state is at each one of these configurations. So when we have some particular configuration of atoms that looks like this, which might correspond to this point inside this line, so some reaction coordinates, so you're here, and you have some system like this. Well, the system, the energy of the system is going to be determined by something. That something is this matrix called the Hamiltonian. Why is it a matrix? Well, in principle, it's a bit more than just a matrix, because you might think of this inside of an infinite dimensional matrix, but it's essentially just has to be a matrix for linearity and all the other reasons that we like matrices. So there's a lot of reasons why it has to be a matrix. a quick refresher on eigenvalues. I can. Very high level. So a very high level picture of what eigenvalue is. So the easiest way to understand what an eigenvalue is just to remember that eigen in German means own, right? So when you think of something that's yours, it's some way of characterizing a matrix that goes beyond the way it looks to you or the way it looks to me. It's something that's intrinsic to that matrix. So these are numbers that are associated with it. So I think the best example of an eigenvalues is if you think of rotation. So you think of rotating something. If I rotate something about an axis, well, if I'm on that axis, it's not rotating at all. And so that would be the eigenvector of the rotation. I don't know if that helps, but maybe that's more of a physical way of looking at it. All right, thank you. Great. Glad to help. Right. So the idea here is that you have this Schrodinger's equation that's telling you how to propagate a system, or it's telling you about the energy of a particular state inside that system. What we should think of this Hamiltonian as is just another operator that we're computing as an observable. The same way we can measure the expectation value of whether it's a 0 or whether it's a 1. We just do some measurement to decide if it's 0 or 1. In this case, we're going to decide whether n is equal to 1, whether n is equal to 2, 3, 4, or whatever the number of different values that this n can take. But they will all be discrete. And that's the idea of largely the idea of quantum mechanics, that they have these discrete energy levels. Okay? Is that at least satisfactory at some high level? Aren't I quantized energy levels of? Yes. Yes, that's absolutely correct. Your question is correct. Or yes, what you said in your question is correct. Okay. So with that bit of mathematics behind us, okay, so we're not going to go too much deeper beyond this in terms of mathematical content here. We will think a little bit more about this Hamiltonian and getting the eigenvalues, but just as more of a cursory look than as an actual computation to give some motivation as to what the limits of electronic structure are. So actually getting these eigenvalues and propagating the system, figuring out how the system responds and how the system is going to change in time is actually very difficult. And the difficulty is highlighted by thinking about what sort of problems people are interested in. So one of the more interesting problems that I got to be involved in when I was in Vienna, University of Vienna in Austria, was there was a group that was working on doing double slit experiments, but instead of doing double slit experiments with, say, an electron, they were doing double slit experiments with molecules. And it was really interesting. It was wave matter interferometry. Basically, you're taking a whole molecule and you're playing the same double slit experiment, and you're seeing the molecule interfere. You're seeing the molecule behave as a quantum object. Yeah, exactly. It is very cool. So this is actually one of the cooler things that they can do. And they came to me to ask some questions about what I could do with electronic structure. And so the molecule they were looking at is this anthracene molecule. So anthracene has 94 electrons. So if we think of computing something with these 94 electrons, well, that's a lot of electrons first off for electronic structure. If you think of this in terms of qubits, we need at least 94 qubits to make a sensible approximation for the system, and probably much more. So probably at least double that number. Okay. But they weren't doing scattering of this double slit experiment with one anthracene. Rather, they were doing it not two anthracenes. Okay, so two anthracenes, we have twice as many electrons. Three anthracenes, we have 3 times the number of electrons. But they were doing small clusters of anthracene. Is the Hamiltonian? I'll give you the size of Hamiltonians in a second. So just wait. But I'll define it hopefully as best I can without going too far from where we're at. But yeah, so let me give you the dimensions next. Okay, so, right. So how do we actually know what the size of the system is? So if we have in electrons, so in this case 94 times the number of monomers we have, and we give each electron so many points it could be, right? So in principle, we'd want it to be continuous all over space and everything would be nice. But in reality, we're using a computer that has numbers, that has discrete numbers. We have 16 digits of accuracy, 16 bits of accuracy, You have 16 digits of accuracy, many more bits of accuracy. In terms of quantum computing, again, we're going to have the number of qubits is going to give us 2 to that number of grid points that we could have if we're using every state as a grid point. Okay. In this case, we're saying we have m grid points, which are just places the electron could be. So you can imagine taking a grid and putting it over top of the picture of the molecule, and then just asking what is there electron at this point, is electron at this point, is electron at this point, how much of an electron is at this point, how much of an electron is at this point, and you're going through and just picking out what all the points are. So if there's n electrons, then there's m raised to the n number of points in the wave function to describe where all the electrons are inside of these m different grids. And then what we have to do is then solve this time-independent equation, which you guys have already, we discussed a little bit, this idea of eigenvalues and eigenvectors. We want to find out what the eigenvalues and eigenvectors are. In order to do so, we can use some sort of eigenvalue algorithm. Okay, so this is called a Gaussian elimination, which you may have heard of if you're taking linear algebra. If you haven't, don't worry. The main idea is to take a matrix, H, and transform it to its eigenvalues and its eigenvectors. In order to do that, whatever the size of the matrix is, you take that size and cube it, and that tells you about how many multiplications, additions, subtractions you'll need to do to figure out what the eigenvalues are. This is basically how you approach an algorithm, how you analyze an algorithm. So Deutsch-Joseph, you're thinking about how many operations it takes for this very simple case, but when we start thinking of problem scaling with size, as in the monomer case, we're thinking about how many it takes for the monomer, then the dimer, 2 of them, then for the trimer, 3 of them, and then for 4 of them, 5 of them, 10 of them. And we want to know how this is going to scale with the problem size. And that will be determined by this m to the n points. And then we have to take that to the third power to figure out what the eigenvalues are. So here, this is taking this idea that if we took, we give every electron for each one of these monomers 36 points it could be at, for whatever reason, just for the sake of argument. Let's say 36 is the number of points that we're going to allow the electron to be. And if there's 94 electrons, then we have each one of these electrons can be in one of 36 places. So we have 36 places raised the number of electrons, which is 94 here, and then that is going to be cubed. You end up with 10 to the 423 operations. So that's a lot, right? The next one's 10 to the 800 operations, and then 10 to the 1,316 operations. So you can see this is what we call an exponential wall. So the problem is scaling exponentially with the system size. So you can see this is getting worse and worse and worse. So when we talk about analyzing computer algorithms, thinking about how hard an algorithm is, we can think if it scales exponentially, there's nothing we can do in principle. If it scales polynomially, right, we can wait. So there's this notion of computers called Moore's law, where the speed of a computer doubles roughly every 2 years. So this is just saying, this has been true for many, many years. It's starting to slow down because of actually running into size limitations, which really turns us towards quantum. But what's that question? It says, what is the actual size of Hamiltonian? Did I answer this question, Mikhail? Yeah, so in any case, this is the size of the system and roughly the number of operations it takes. And you can see this becomes exponential, and it becomes a very costly procedure to actually accomplish. So this brings us back to where the last time I was here, discussing this idea of Schrodinger's conversation piece, where you have the underlying physical laws necessary for the mathematical theory for a large part of physics and the whole of chemistry are thus completely known. The difficulty is only that the exact application of these laws leads to equations much too complicated to be soluble, right? So that's what we're seeing in the previous slide. M to the n is not the matrix size, so m to the n is the dimension. So it's m to the n by m to the n. Matrix. Ah, good, you got it. Yeah, okay. So that's the matrix size because you have a vector, and the vector needs to multiply that matrix. So if the vector's d-dimensional, you need a d by d matrix to multiply to transform it correctly. In this case, d is n to the m. Okay. So here's where we ended last time, talking about this idea of you have this physical system that we can control. We're going to use that to analyze these questions. But now we're thinking about this from the other direction. We're going to assume that we have a quantum computer, and we want to understand something about this large part of physics and the whole of chemistry. This is 1929, he's saying all these things. So with that Schrodinger's conversation piece, what we can do is start thinking about how do we actually apply this in terms of what we understand of quantum computing. And this is where we get into this idea of computation versus simulation. I think this is a very deep way of thinking about quantum computing. When you really think of the difference between doing a quantum computation and the difference between, doing classical computation and a quantum simulation of a system are not at all the same thing. So this is an example that I like to use inside of my talks, thinking about a car accident. You have a car accident, okay, it's terrible. People want to know what happened. Is people safe? You know, what happened to the crumple zones collapse, the airbags deploy, how much forces were applied to the person. Okay, so all these questions you want to ask. And what you can do, and what I've assigned in classes before, is actually just a bunch of harmonic oscillators. So these are just springs. So we have Newton's law. If you have kx minus kx equals the force. And so you take all these different equations and you start saying, well, the bumper has this spring constant, and the suspension has a spring constant, and the metal sheet has a spring constant. You end up with a bunch of constants. You need to figure out how all these constants work together to see how this thing will collapse. Right? So when you apply so much force, how does this whole thing collapse? Okay. This is a schematic model. And that's a lot of mathematics you'd have to put into this to actually be able to solve it. And now, so what we're going to do is think, instead of solving it, let's think if we did simulation. If we did simulation instead, we're not going to do any of the mathematics, right? This is crumple zones, all this stuff, with a bunch of spring constants, we estimate all these things, we do differential equations, and F equals ma, and you know, how long did it crash, and how hard was the wall, et cetera, et cetera, et cetera. Let's say we just round all those things out, and we just say we're just going to take a car, we're just going to crash into the wall. So I'm going to get my car, this van or whatever it is that I want to test out. I'm going to initialize it, so I need to get a van first. And I'm going to propagate it, so I'm going to smash it, and then I'm going to do measurements as it's smashing. Okay. So really, another way you could think of this is that we're doing both measurement and propagation at the same time. So you initialize your state. So this is, if you think of this in terms of quantum simulation, we have some initialization of our wave function. Then we have this time evolution due to the Hamiltonian. And we want to do some measurements to get out some properties of that system. We want to know what happened, right? So if you even look at these pictures here, these look very much like spectra. But these are actual just the data that was collected from this collision. But again, it looks like spectra. And what we want to do with quantum simulation is obtain model spectra, right? And if you don't know what that is, not so important. We just want to know properties of the system. We do measurements of the system that we're interested in by evolving the system rather than actually computing every detailed equation. We're just going to map the system onto the one that we're interested in. Right. So one of the important things about quantum computing that sometimes gets pushed aside. So this notion of doing quantum simulation is hindered by a very important aspect of quantum computers that a lot of times doesn't come up as clearly as it should. So the idea of doing the propagation, so with the quantum computer, we can do the propagation efficiently, right? This is the whole idea of doing unitary evolution. So we have all these unitary gates. There's a lot of tricks to combine these unitary gates in a way that we can do the time evolution in a way that matches the system we're interested in. So you can imagine that basically have like a prototypical car, just some model car, whatever. And if I start putting details on that model car, all the material, all the raw material, then I can make a model of that car inside of my quantum computer. And I can crash into the wall, and then I can see what happened. Instead of a car, we do this with a molecule and ask questions about the molecule. The problem is that if we want to know about a molecule in a very particular state, it may be very difficult to generate that state. So if we're thinking about doing this idea of simulation, well, we're going to need to repeat it several times. Okay, we need to repeat it multiple times to get some statistics, or maybe we didn't get the data on the first crash, or whatever. We want to know what's the probability that they fly out, so we need to repeat it multiple times to get out more information. But if you have a car that costs $1.9 million, it's a very expensive way of doing computation, right? And this is one of the major problems of why you can't just apply quantum computing to every problem in quantum chemistry, is because you still have to prepare the state. So preparing the state is essentially making this car over and over again. And this may be very, very expensive, even prohibitively expensive. And so that's one of the limitations of where you can and can't use quantum computers. Okay? It's admittedly a bit cursory, but this is a 30-minute talk. So I want to give you some high-level takeaways of what we're looking at here. And the takeaway that I want you to take away again is that we have the Schrodinger's equation, which is either solving an eigensystem, so this is getting eigenvalues, eigenvectors, or propagating a partial differential equation. In both cases, they end up being equivalent for reasons that are not really important. This electronic structure problem, don't have to worry too much about the details there. But one of this no free lunch principle of electronic structure is that there's no perfect way to compute every property of every system. Like it's just, they could be very difficult. They could be arbitrarily difficult. So you can imagine that every approach to electronic structure has its limitations. And the main idea, the big idea, the largest idea, the thing you should take away from this, and the thing you should understand about quantum simulation in general, is that what quantum simulation is is taking your quantum computer, applying gates at the right pattern, the right cadence, the right repetition in order to get your quantum system to look like another quantum system. Be that a molecule, be that a solid, be that whatever it is. And once you have that system effectively inside your quantum computer, then you're doing simulation rather than computation. Right? So computation is just how to put it onto that quantum computer. Once it's on the quantum computer, you just let it evolve under that Hamiltonian. So once you map this Hamiltonian onto the system and you map on some initial state, you just let it do the quantum thing. There's nothing that you need to do, right? It's a quantum system, so to simulate itself. And this is actually what allows quantum computing to be efficient, to be a very huge source of impetus of why people are building quantum computers, is to do this idea, to actually take a quantum system we want to know something about, map it to the quantum system that we have control over. And that's the story. Any questions? Any more questions, rather?
Can you go over this big idea a little bit more, because I'm not getting it. So it's basically you're just saying, okay, well, I can model this one quantum system on a computer. Now I want to just somehow change the model to do this other system.
Yeah, exactly. So maybe I can say a few more words about this. Great. So no, I don't want that. Yeah, so the idea there is that you can, there we go. Yeah. So your question, let me turn off my camera, it's really weird seeing my nose. Yes. So your question was about this Hamiltonian. So if we have these unitary gates, you have U, might be a Hadamard gate or a C0 gate. And then maybe a rotation by Rx, and another C0, another Hadamard. Maybe some more lines, right? So you have all these different things you can start putting into your system, different gates, and you have some other gate here, some gate here. But at the end of the day, all this is just some gigantic unitary. This unitary is what's going to also be doing the propagation of our system. Right? So the idea is that this unitary, for the system we're interested in, this might be a molecule. And what we're going to do is map that molecule's dynamic to our quantum computer. Okay, so the idea is that whatever unitary the system would do naturally, there's an efficient way to map it onto these quantum gates that we've been discussing during our course. Does that help? Or
when you say mapping, are you really meaning that we're going to put it through a gate and have a gate? What do you mean when you say you're mapping it onto the quantum computer?
Yeah, that's a good question. So the idea is that these gates here, so whether I have a Hadamard or Z or whatever gate this might be, and where I put my C0s, I'm going to put in all these gates in order to mimic the dynamics of this unitary. So this is the idea of mimicking what we had on the real system.
You're building a circuit that mimics your real world molecule.
Exactly.
Oh,
that's
okay.
Precisely right. That's exactly what we're doing. So this is U comp, and this is U molecule. And if you do it right, and this is guaranteed by the way quantum computers are constructed. So when you think about this, the red one, so the quantum computer itself is some quantum system that evolves in time. You take a quantum system, but now I can control this quantum system that I can evolve in time. I can control it through some sort of pulse, through some sort of coupling matrix, by calling an RZ gate. I can control it by doing a Hadamard on qubit 1 and doing some black box. There's some, some, I don't know, some T gate on qubit number 4. I do all these gates inside the right sequence, and what I'll get back is effectively this unitary for my molecule or for my solid or for my whatever system I want to simulate.
Okay, but the critical point here then would be that you have to already know how to very accurately model this molecule that you want to do.
Yeah, that's not so hard. The critical point, and that's exactly right. But the critical point is at the time evolution. So how long it takes for the quantum computer to do it is going to be proportional to how long it takes the real system to do it.
It is?
Yes, ma'am.
Speed up the quantum computer and say, run faster.
So the molecule itself is going to be determined by some time evolution, but it's a quantum system that evolves in time. And the quantum computer is also a quantum system that evolves in time. You know, be it actually maybe a molecule, right? There's molecular quantum computers. You know, you could trap ions. Those ions are trapped, and then that allows you to manipulate the ions. And so you can imagine that I want to simulate an ion rather than just have it there.
So the quantum computer has a time dynamic, if you will.
Yeah, exactly.
Modeled after the real world dynamic.
Yeah, that's exactly right. So the quantum computer itself has no dynamic itself. It has a dynamic that you impose by applying the Hadamard gate.
By building your model.
But beg your pardon?
By building your model.
Exactly, by building it up, right? So you actually construct the gates, you pick which gates to do. So once you know what your molecule looks like, then you have some sense of which gates to apply, what order they have to be applied, you know, the way to map the model of the system you're interested in onto your quantum computer. And you just let your quantum computer evolve like a quantum system. And because it's evolving like a quantum system, the amount of time it takes to do that evolution is going to be proportional to the time it would have taken the real system to do it.
Okay. Oh, gotcha.
And that's something you can't do classically. Classically, it's impossible to actually have this. So classically, you know, so T classical is much, much greater than T molecule, right?
Not seeing whatever you're writing.
You are not, or you are?
Not.
No? Are you guys, is everyone not seeing it?
Oh, there it is, down at on the bottom right.
Yeah.
Yeah,
So it's just that,
the bottom of it.
no.
Sorry.
Okay. So we'll move it.
So you were using this modeling. Were you actually modeling the atom or the atomic structure?
Well, the electronic structure, but yeah.
The electron. And so what kind of information were you able to find out then?
So at the beginning of the slides, I tried to give some notion of what you want to know. So you want to know about what energy the molecule has at different shapes and different sizes and different configurations. And those configurations will then tell you about whether a reaction will occur, whether a reaction won't occur, whether the molecule is stable, whether it's unstable. Does that clarify? So, yeah. So if we want to know, like if you took some molecule, we want to know, is it going to break apart if I turn up the temperature? Is it going to break apart if I hit it with a photon? If I hit a photon at this frequency, will it break apart? If I hit it with a gamma ray, will it break apart? If I shake it, will it vibrate more? Things like that. You can start asking these questions because I have this model system. The same way that I have the model system that I have this car, I can crash it. I can hit it from the side. I can hit it from the back. I can hit it whatever direction I want because it's my model of the car. Right? Same thing here. And once I have this quantum computer, I can model it and have it do whatever I want. I can change the dynamics. So maybe I have a molecule that evolves according to some system, some red U, but maybe I don't want it to evolve that way. Maybe I want to add in some other perturbation that might be of interest. Yeah. So the critical point is that the quantum computer is doing the time evolution in proportional amount of time it took the system to do it. The classical computer is always going to take much, much longer to do the same time evolution. As far as we know, I don't think there's no how many qubits you need to get hydrogen, hydrogen's energy levels. So you can do it with 2 qubits, and in fact, maybe even 1. It's really cheap approximation. So the thing is that you're discretizing the system in ways that are going to cause errors, and those errors don't necessarily, those errors will be there, but you can discretize the system. So in the example that we had in the beginning where we had these monomers, where you have M, oh, I just gave M as 36, I just picked the number, but in principle, M should be infinite, right? Okay. More questions I can help address? I will also tell you guys all that a large part of the packages, so the tutorial, so after you finish everything here, we'll go over Schur's factoring algorithm tomorrow, or I think the end of the week, or whenever the last module, we'll do Schur's factoring algorithm. But from there, if you want to learn more about how quantum simulation, quantum computation, all these things work, quantum simulation works, a lot of the tutorials inside of the different packages, Microsoft's package, IBM's package, Google's package, a lot of them are focused around this idea of doing quantum simulation. It's a very large field, a very active field where people are thinking very much about how to map these dynamics. This is a very active field about how to map the dynamics, how to do so efficiently, how do you actually pick out which gates go where, how do I extract information, and all these sort of things that are details that I didn't get into. These are active areas of discussion.
I have a dumb question, if I may.
Yes.
You mentioned Gaussian elimination, and what form of, or what kind of math is that? So if I wanted to go learn more about that.
Linear algebra.
Linear algebra, thank you.
Yeah, so we gave a very brief introduction to linear algebra here. We just talked about how to add vectors and how to multiply matrices. The next step from there would be to learn what are eigenvalue eigenvectors. So this is the next step in a linear algebra progression. But again, this is a 2-week course, so we can't cover everything.
Yeah, no problem. Thank you.
But yeah. Okay.
All right. Yeah, agreed. There's no such thing as a dumb question, especially, you know, this is all pretty abstract, so always good to clarify as much as possible.
Yeah, high level, so yeah, feel free to ask as much. All right.
Awesome. Thanks so much, James.